went over. The PowerPoints are up there. I modified them some this morning, so I'll try to upload the newest version this afternoon. Well, we compared electronic sensors or electrical sensors to us, right? And then talked about the basic makeup of an electronic or solid state sensor. And then we looked at basically at one bit, all the way in digital we refer to as a bit as a single binary digit. So so these things are made up of a bunch of ones and zeros. And what advantage does digital have over analog? Nobody in here knows? Well, we can represent them a lot easier too. So we got to represent numbers in electrical quantities. So analog would be like me having a light dimmer on an incandescent light, and I'm trying to send you information, right? You understand that? So every intensity would mean something different. Or if I had a flashlight that had 10 different combinations on it, when I turned the flashlight on all the way, that would be 9. And if I turned it off, that would be a 0. And I go over here on this hill over here, and you're trying to interpret the intensity of the light. That would be almost impossible, right? But how far could I get off and you could tell if a flashlight was on or off? A long way, right? Because we're not dealing with intensity anymore. We're just dealing with on or off. So this is what we can do with digital is we can represent information with voltages or currents. And we have current loop, and we have voltage. All our sensors here that we're going to deal with is voltage output sensors. So in binary, we just use this might be information, but I could send that with lights, right? You understand? So I could say, okay, I'm sending this, and I'm sending it at a certain rate. And so what we would do is, if it was what we call synchronous information, is I would come up here, I would write something up here, and then I'd beep, and you'd open your eyes, and then you'd close it up, and then you would write it down. Well, that way, if I timed you right, you understand, we would have very little chance of error. But I could use all types of different things. Of course, the main two ways we use to represent these would be volts. So if we're using volts, to spell it, then here, of course, this would be some voltage level. Let's say plus 24, and then this right here, I would give you a 0. And now I can really send information. We can send it a long way, and we can send it accurately, because we're not dealing with precise voltage levels anymore. We're just dealing with is the voltage there, is the voltage not there. And like I said, a PLC, the 24 volts, we're using 20 plus 24 volts, and it'll recognize anything above 20 volts as a legal one. So now we got a 4-volt margin that we could be within, our sensor could be within, and still be able to recognize that as, a true output. So this is the biggest disadvantage of digital over analog, is that we can be more precise with our data. We can store it. It's so easy to store voltage levels. Somebody brought up a battery. So a battery is a perfect example. What can I do? I can't store AC in a battery. Now, give it a try, and make sure you give me your next of kin, because odds are the battery's going to blow up on you, right? So we can store it. We can use it later. We got these little capacitors, anybody in AC, and one of the things they love to do in DC is store a charge. So that's exactly the memory in this computer. When I say I got 8 gigabytes of memory in this computer, they're all just tiny capacitors. That's all they are, that we charge up. That's all they are to it. But it's got to be DC, right? So the big advantage of these digital sensors is they're either what? They're either off or on. We're not trying to translate an exact precise voltage level, and we have a margin. Even Alabama Power or TVA, whichever one you're on, don't guarantee you 120 volts. They guarantee you 120 volts plus or minus 10%. So technically, you could be getting 90 volts at your house, and your devices still should work because you're within the watts, you're in the guarantee. So that's what's nice about this. So this will be just a single bit. So we call these things, each one of these digits in a binary, in binary, we refer to those as bits. And then groups of 8 we call bytes. Groups of 16 we call words. Groups of 32 we call it, in PLCs we call it a long word. We call it a double word. We have names for these. So all we're dealing with this single bit A/D converter is just very, very simple, right? You understand? And most of our control is dealing with is something there or is something not there. And we'll look at those. And then we looked and saw that if we came over here and added, if we made this a rheostat, then we have the ability to adjust the sensitivity or the threshold on where it trips at. Sensor output, we looked at that. Current loops, we looked at the single-ended and differential. All our sensors that we're going to be dealing with in this class are single-ended. And we talked about single-ended would be it's very simple. Then we look at differential, where we have new electronics. This came along without this. These differential amplifiers revolutionized the way we send data. So USB uses differential signaling. Ethernet uses differential signaling. There's a lot of devices now that use differential signaling, so we can almost ignore electromagnetic interference. Looked at current loop, and then we're looking at syncing and sourcing. These are the symbols, and I just did these guys. So if you're looking on Blackboard, they won't. On Blackboard, they won't be on there. So these are the symbols in motor controls. We have generic symbols for the solid state or electronic sensor. And this is what we do. We just draw a diamond shape and we put the symbol for a normally open limit switch in there. That's the basic symbol that we use for in motor control. In the PLCs, we have more precise symbols for these sensors. So we'll look at those and make sure we know those. So this would be a 2-wire sensor. So the sensor actually powers up through the load. So these guys are going to drop a voltage across them. And here we're going to measure probably around 4 to 6 volts across this. Because they got to create power, right? You understand? So they got to drop a voltage. Then we have a 3-wire sensor. These guys power up. So they actually power them. They can't handle it, or this would be especially true for lower voltage applications like PLC. So most programmable logic controllers now currently power up on 24 volts. And I can't afford to lose 4 volts in a sensor, right? You understand when I bring it into a PLC, because right off the bat, I'm almost out of the limit. So these sensors are powered. So these are 3-wire sensors. So we'll have one wire that connects directly to L1. So we'll have another one that connects directly to L2 or power. And then we have an output on our load. And then we have a 4-wire sensor. So these are simulating. So that's similar to something, right? These are simulating. This right here is not a switch. It's usually a solid state device like in here. It'll be triax or it'll be a relay. Some of our sensors have relay output. So you can actually hear them click when they become true. So these are powered up. So when these things turn on, you're going to get almost 0 volts. You're still not going to get 0 volts unless they got a relay output. Because they're solid state. They use electronic devices like triac outputs. These some people call them solid state relays because they will switch on and they will pass AC, which is pretty neat. These guys, but they still have to drop a voltage because they're not a switch, they are a semiconductor. So these guys, but we're going to get down in the millivolt range here on a powered system. And then we have a 4-wire sensor, and this simulates a single pole double throw. We talked about that in class the other day, right? So it's going to simulate one of these. So that means we'll have a output that is false when the sensor doesn't detect it, and then we have an output that is true when the sensor doesn't detect it. These are called 4-wire sensors. And the standard color code, I'm not going to say you're going to run into something different, is the wire that connects toward L1 are positive in DC. This is going to be brown. And then the normally open output is going to be black. The normally closed output is going to be white. And then the L2, or the one that goes over to the negative in DC, will be blue. And so this will be pin 1, this will be pin 3, this will be pin 4, this will be pin 2. They label, if they actually label the pin number. I'm not going to say you might not run into something different now, but this is the basic industry standard. So over here on the 3-wire sensor, this should be brown. This should be blue. This should be black. And on a 2-wire sensor, this should be brown. And this right here should be blue, because it points toward L2. So your pins, your power pins are going to be brown and blue. It's just that this one powers up through the load. So this sets it off. So the first sensor that we're going to deal with is an inductive sensor, and it's going to be a 2-wire sensor. So it's going to power up through the load. So we can't hook these 2-wire sensors. We can't hook a bunch of them up in series, right? You understand that? And why? One line goes up. Yeah. One line goes up. Well, that would be true of any of these. So if this sensor died, then everything would be here. This would be died. That's the point. But that's not why we can't hook a bunch of these 2-wire sensors in series. And why is that? So I got 120 volts. I put one of these things. This thing drops 6 volts. That means over here I have 114 volts. I put another one over here. It drops 6 volts. I put another one. It drops 6 volts. And now my output don't work anymore because I've lost so much voltage. So single 2-wire sensors, you got to be really careful about what you do with them. So normally, if we had to have multiple sensors, we would just come over here and have this one run a control relay, and then I'd come over here and have another one and run a control relay, and then that way we would combine and then down, if we call it CR1 and CR2, then we'd come down here and use contacts to hook in series. Does that make sense? So this would be CR1, CR2, or how many of that. And this way we don't sacrifice or get to a point where sometimes it might work and sometimes it don't. Did y'all I don't think in motor control, you did the troubleshooting lab where they put the 2 light bulbs out there, and sometimes it works, sometimes it don't, because when you put the light bulbs in series, sometimes the control relay will pick up and sometimes it don't. And that's the problem. We get to the point where it's going to be intermediate, and intermediate problems are the hardest to fix. If you're a technician, you like something to break, and you like for it not to work. You don't want it to work. We had a scale down at Columbiana where they made railroad wheels down there, and we would come in around 8, and they'd call in and say the scale's not working, the electronic scale's not working, and we'd get down there and it would work, and we'd stay down there 2 or 3 hours, it worked the whole time. We'd come back the next morning, we'd come up and they said, the scale's not working. And we'd get down there and it would be working perfect. You know what it was? It was the wintertime. And at night they didn't have any heat in the shed, so what was happening is it had a open, that when they designed it, they did something they shouldn't have done. And they didn't have heat in there, and the circuit that worked wouldn't work when it got too cold. So we finally figured that out. We had an electronic scale down in, out in Opelika, that the printer wouldn't work. And we'd get down there and we noticed when a person stood in front of the window, it worked. When the person moved away, it didn't. And what was happening, it had a photoelectric sensor down there and the sunlight was getting into it. And so, we figured that out. So how did they fix that one? We came in and we took an input that they didn't hook up, and we connect on the other one. We hooked it up to I can't remember if it was a positive or negative. We had to hook it up on the scale down in Opelika. They just taped a piece of cardboard up on the window so that light wouldn't shine in there. But those are really, really hard to fix. So intermediate problem, you know. But these and that's what would happen if you put 2 in series or 3 in series. Sometimes it might not work, and sometimes it might. So these 3-wire sensors, we don't do that. I'm sorry, 2-wire sensors. 3-wire sensors we could, because those don't drop a voltage, hardly any voltage at all. 3 and 4-wire sensors, we look at that. Electronic sensors usually have only one contact. So normally, if we need multiple contacts out of the electronic sensor, we'll let the electronic sensor energize the control relay, and then we use the contacts off the control relay. So solid state sensors usually only have one contact. It could be a single pole, single throw, or a double pole, double throw. I mean, a single pole, double throw. Y'all understand those terms, right? We okay? Yeah. 3-wire sensors will only provide one single pole, single throw electrical contact. 4-wire sensors would be a single pole, double throw. So we'll have a normally closed and we have a normally open. So the white would be true, the white wire would be true when the sensor doesn't sense what it's supposed to sense. And then the black wire would be false. Go ahead.
Can you draw the symbol for a single pole, double throw?
I thought I just did it. So this is a single pole, single throw. And then this is a single pole, double throw. So what we have is so this right here would be the normally closed, and this right here would be the normally open. So most sensors the black wire is a normally open.
And the throw is just how many switches?
The throw is how many switches are controlled by the same operator. Gotcha. Okay. So in motor controls, we would come up here and we would draw it like this. And then I'd come over here and draw another one like this. And then I'd put a dashed line between them, which means they operated by one operator. This would be double pole. And then each switch has only got one position. So this would be a double pole, single throw. So understand, so the poles are the number of what? The number of switches that are controlled by the same operator. And relays are rated like that too. They'll say it's a 5-pole relay. And what that means, there's 5 contacts. They don't usually put the throws because that's what you'll see that. They'll say it's a 5-pole relay. And that means there's 5 sets of contacts in there. So good question. Any more? So simulated, so relay. So the sensors put out relays. I think our temperature sensor and our pressure switch has relay contacts. So that means when they sense, they got a little what we call, I should have brought one up. These little relays are very, very small. what's nice about a relay, what would advantage would the relay output of a sensor have over a solid state output? Anybody know? You can connect AC across them, you can connect DC across them, and you would look at the rating. It might pass 120 volts DC, it might pass 24 volts, this is AC, it might pass 120 volts AC, it might pass. So what's nice about a relay output is that it doesn't define what voltage you pass through them. So everything that we're dealing with is 120 volts. So some of our sensors have relay outputs, which means if they got relay outputs, they'll pass 120 volts, or they'll do what? They'll pass 24 volts. These are dedicated. So SCRs, this would be DC, tracks. These guys are AC, and then these guys right here are DC. The biggest problem we have with relays is their speed of operation. They don't operate extremely fast. I'll take motor control. And you told a relay to energize, it didn't energize just like that because it's got to generate that magnetic field and it's got to pull that armature down and make contact, right? And then plus they're electromechanical devices. So electromechanical means right off the bat they have two ways that they can take. So they can tell mechanically or they can tell electronically. The big advantage is that it doesn't determine what type of voltage you apply to the switch that goes to the actual switch itself. So these are very, very so you take PLCs, the PLC that we have for PLC 1 uses relay output. We're using DC on what we do this as well. If you look at one of the 1100 PLCs, they have relay outputs and they switch 120 volts AC. So that's the big advantage. And this would be something that if you just buy a part number or something like that, it's not going to be something that you're going to have to understand. But you know, the company that makes your sensor might go out of business, and if they go out of business, then what do you got to figure out? You're going to figure out how to replace it, right? For the folks you know. Are we okay? Questions? So this could be a PLC. They're calling it a relay, but this could be a program controller, or here we're going to use relay lights. In DC, when we're dealing with these NTN and PNT sensors, we're very concerned on whether they're a sinking sensor or a sourcing sensor. And most companies make both of them. So you can't depend on the manufacturer of the company. So that would be like, you know, going to an electronic supply place and saying, I want 100 ohm resistor. What's the problem when you say 100 ohm resistor? So we had, I think y'all probably heard the story before. We taught a class in power supply design. It was really neat. And at the end of the class, once they got their power supply built, and once they finished it, they were supposed to spec it. They were supposed to come in and see how much current it could actually put out before the output dropped down below a certain level. And more than one student came up, and one of the things they were supposed to do was hook up a 100 ohm resistor. And they came up and they'd say, well, Rich, something's wrong with my power supply. It keeps burning up these resistors. So what they did is they went and got a 100 ohm resistor. And what's the problem? Well, not the tolerance. It wasn't the tolerance that was burning them up. So what are resistors rated in? So when you order resistors, you got to know certain things about that resistor. You just can't say, I want a 100 ohm resistor. And so if you say, I want a 100 ohm resistor, and if you're dealing with a person, they're going to say, okay, what else do you need on this resistor? So what's resistors rated in? Number one, ohms, right? And number two, somebody said it, watts. And number three, tolerance. So it's just like in a sensor, you say, okay, I need a 3-wire sensor. I need a 3-wire, proximity sensor. And they're going to say, okay, but you got to know more things about the sensor, right? You got to know what type of output is it used. Is it triac? Is it SCR? Is it relay? Is it all these other things you got to know about the sensor? So we have two ways we can hook up sensors in a system. Once it's established in the system, then you got no control over it. It's what does the company use? What do they use? So we have what we call a syncing sensor. Okay. And what we're going to do is we're going to look and see what the sensor is connected to. So here's the sensor. And it's a 3-wire sensor. So we got brown and blue. That's our 2 power leads, right? You'll understand. So here's my PLC or my relay. This guy right here uses a wattage column. He uses minus. This guy up here uses wattage column. He uses a plus. So what that's saying is that since this guy is connected to minus, then this guy here has got to put out a plus. You understand? Yes or no?
No.
Well, to get current to flow, so we come over here and we got this, and then we'll use the PLC, and then I got the input of the PLC. It's going to be referenced to a voltage level over here. Right? You understand? And my sensor is going to connect over here somewhere. Sorry. In fact, this would probably be better if I do it on another slide. So here I've got a wire, here I got a wire. Here I'm going to have my PLC. My PLC inputs are going to be connected to its common. And then I've got a common over here I'm going to connect to my sensor. Okay, so what if this common over here is minus? Then what do I need over here to get current to flow? Here's my sensor. So here's my sensor. I got to have a positive over here to get current to flow through it. Okay. All right. So all my sensors would have to be connected to a positive common. Common is not necessarily ground. Well, what would happen if I ran into a system and these engineers decided to do this? So what if they decided to do this? So one time it was like this, the other time it was there. So what type of sensor would I have to have here? Well, if I come over here and do this, right, you understand, then I've got to have a sourcing sensor because when it passes through, it's got to give me a what? It's got to give me a plus. Right? You understand this? Yes or no? Okay. I see these bobbleheads back there. I learned a long time not to pay any attention much to that. Now if I come over here, so what did I have there? I have a minus, right? So what did I have last time? Sorry. So what did I do? Okay, so this is a plus and this is a minus. So if this is a minus, then this sensor's got to give me, did I say that? This guy here's got to give me a plus, right? So I did it wrong. So let's swap it around. I think I just said it wrong. So if this is a minus and this is a plus, then my sensor is going to give me a minus. If I said it right. That makes sense? Because we got to have what?
So positive coming out of the sensor.
Sourcing. Thinking. That's exactly right. And so over here, a T&T sensor is a sourcing sensor, and an NPN sensor is a sinking sensor. And once you get into digital, this term actually came through digital electronics, sourcing and sinking. And so they moved it over to PLCs, but they don't explain it very well, right? You understand that? And exactly how the sensor is made up, I think that might be on one slide. So the problem is, if this is a positive and I buy a sourcing sensor, it's going to try to give me a plus into a plus, right? You understand? And there won't be any current flow through my PLC. So this is why it's very important when you deal with these PLCs to know what type of input that they use. And that's some of the things when you buy them, that's what you specify. And most of these companies, everyone that I've ever seen, gives you all that information for free. So if you get into a company and it's got a Siemens PLC up there, and you look at the number and you just search for the operator's manual or on that PLC, you'll be able to get it, and it'll tell you right off the bat whether the inputs are what, sinking or sourcing. And some PLCs allow you to establish it. So we've got a PLC, we got two PLCs over there in the lab. We have a MicroLogic 1500 and we have a MicroLogic 1100s where you can configure the PLC's inputs to be sinking or sourcing. And you can configure the outputs to be sinking or sourcing so this is very, very important when you buy these solid state sensors. This won't come into play. Well, I guess if you get into motor controls and the company you go decides that there's nothing that says the positive has to be L1. There's no rules that says that. Just because your car uses that doesn't mean any company is going to use that. So that's something that you need to understand if you get out there and they use a lot of DC stuff. What do they consider to be their common? What do they consider to be L2 and L1? Does that make sense now? Everybody okay? So if the programmable controller or the system, if the loads use a positive common, then I've got to use what? Use a positive L2, then I've got to use what? I've got to use a sinking sensor, right? If it uses a negative L2, then I've got to use a sourcing. So if I hook up those wires backwards, then it's not going to work. So what type of sensor would this be? So my PLC, my PLC or my relay is using a negative common. So this guy right here's got a source, right? You understand that? These are 2-wire sensors. So 2-wire sensors, we don't worry about that. And if it's DC, you got to honor this. If it's a DC sensor, you got to make sure the brown wire goes toward plus, and then the blue wire goes toward the load. If it's an AC, guys, it makes no difference. If it's an AC sensor, it's still going to be brown and blue, but you need to get in the habit of taking the brown wire and put it toward L1, and then the blue wire toward the load. And that way you keep a standard, whether it's DC or AC, you wire the sensors the same, right? Does that make sense? And this is the problem we have. So any low volt application, you probably won't see any 2-wire sensors. On high voltage applications, these guys are see a type of these. In fact, the first one that we're going to use is an inductive sensor, and it's a 2-wire sensor. But then we're going to move over to a photoelectric sensor, and it's a 3-wire sensor. And when you measure the voltage drop across that sensor, it's going to be very low. When you measure the voltage drop across the 2-wire sensor, it's going to be relatively high. Okay, we already looked at this, the wiring, right, and color code. Are we okay here? Yes, no? And the color code doesn't change. And one of them would be a thinking enforcement. So notice the way the loads are connected. So here the loads are used in a negative column. And up on top, the loads are used in a positive column. We okay? Question? These are the symbols. I'll try to get, these are not up there. We need to know these. I'm going to try to make them bigger because this is sensors. And these are the sensors we're going to look at. We're going to look at more than this, but this is, so in programmable logic controllers, we have symbols that represent what type of switch it is. So up here, is this a photoelectric sensor? Is it an inductive sensor? Is it a capacitive sensor? Is it a pressure sensor? We don't know, because in motor control, the generic symbol for a sensor is just a diamond shape. When we get into programmable logic controllers, they move over to the International Electromechanical or Electrotechnical Commission IEC symbols, which are international symbols. And then we'll come in where they actually come in and identify the type of sensor it is. So over here, all your sensors are in a square. And then it's got the little triangle here again, with 2 dashed lines on it, indicates it's a sensor. This indicates that it's only got a single pole, single throw, normally open. And then this little symbol right here identifies what type of sensor it is. So we'll come back when we go through these to make sure we see it. So we have inductive sensors, capacitive sensors, optical sensors, magnetic sensors, ultrasonic sensors, and then a normally open and normally closed contact. So there's probably some symbols for more. Of course, you can go up there and look these up, if, or especially on your diagram if you see one that we're not going to cover. So we're going to cover pressure switches. So this is a pressure switch. Single pole, double throw. Can you see the little symbol right there? Or single pole, double throw. So this is probably going to be a 4-wire sensor, even though they don't show the other wires, so it must not be connected. So I'll blow these up and make them bigger, and I'll put them up on the website. So you can see these guys get more detail on what type of sensor they actually are. So we Stonebridge, we'll look at this. The problem, we have a lot of sensors out there that change their resistance relative to what they measure. And we can't send resistance over wire, right? You understand that? So the method we use is a technique called, we can use what we call a voltage divider. So I could come over here and put a resistor. So this is plus 24. Then I can put my sensor down here, and I'm going to draw it as a rheostat. And then I could take an output right there. And then if we came over and put a voltmeter right here, then as the output of the sensor went down, the voltage would go down, and if the output of if the resistance went up, the voltage would go up. If I wanted it to work the other way, then I would come up here and put my sensor right here. So on the top one, if the sensor's resistance went down, my output voltage would go up. If the sensor's resistance went up, the output voltage would go down. So here, this would operate in the opposite direction. This right here would operate in. So if ohms goes up, then my output would go up. It's this way. If R goes down, the output would go down. Over on this one, if R goes up, the output would go down. And on this one, if the R of the sensor went down, the output would go up. So it depends on what type of system you're in. But the problem is, if it's a temperature sensor, or if it's a weight sensor, or if it's a pressure sensor, then we would have to figure out what, so if I have no pressure, this guy right here would still put out a voltage. So this is one way. This is a voltage divider output. This is very, very simple. So what we want to do is we want to come up with a way that we can establish a zero. So we're going to use something that's very, very widely used. It's called the Wheatstone bridge. And everything, so this was originally the way it was developed. And some people draw it like this. And this up here, this will be power. Let's say this is plus DC and minus DC. And we take our output right here. I like to draw it like this. It makes it look a lot simpler. This gets into a way that we would draw it in DC. Let's see, plus, minus. And then we'll take our output right here, and it's going to be a voltage output. So this is the Wheatstone bridge. Let's say I have plus 5 volts up here, 0 volts. I said, I didn't think I was going to have to do this anymore. Oh. And let's say this is 10K, and this is 10K, and this is 10K, and this is 10K. What would my meter read? How did you come up with that? You know. Yeah. But somebody don't know why. Mario knows why. Why would it measure 0? Yeah, because what would happen is we learned in DC that resistors of the same value drop the same voltage, right? So let's do 10 volts instead of 5 volts for this. Maybe we won't be dealing with fractions. If they drop the same voltage and the total voltage has to be applied across the circuit, then each one of them has to drop 5 volts. This is what I'm going to use this one down here as our reference. So that means this would be plus 5 volts. This right here would be plus 5 volts. And what's the difference in potential between a plus 5 and a plus 5? Huh? 0, yeah. A lot of people want to say 10, but that would be if one side was plus 5 and the other side was minus 5. So our meter would measure 0. So what we can do, and if I call this R1 and R2, and I call this R3 and R4. If the ratio of R1 divided by R2 is equal to the ratio of R3 divided by R4, then the output would be equal to 0. I don't care what they are. They don't have to be the same value, they just have to have the same ratio. So if these ratios are the same, the output would be 0. That's if it's balanced. That's why I said, so it's equal. It's equal. If they're not equal, then we would get a voltage. So what we can do with this guy is I can come over here and I could have my sensor here. So this is my sensor. We'll make it variable. So this is a sensor. OR ridge. And then I can come over here and make this my calibrate. So what we can do is we can have our, let's say it's a temperature sensor. We're going to look at a temperature sensor called a thermistor. And it does exactly what it says, thermistor, so it changes its resistance with temperature. And we can take the thermistor and put it into a glass of ice water, and then I can come over here and adjust this until that measures 0. Now we have a reference to 32 degrees Fahrenheit or 0 degrees Celsius, right? You understand? And now when the resistance changes, it would actually mean something, because with a Wheatstone bridge we can establish a 0. So a pressure switch, I could establish a 0, right? You understand? A pressure switch, a pressure sensor, because it's going to sense 0 all the time. In fluid power, you'll learn that pressure gauges are two things. One of them we call a, dang, I forgot, I had it come up. One of them we call absolute pressure, and one of them we call gauge pressure. Gauge pressure takes out atmospheric pressure. So if you go out and look at a pressure gauge and it's sitting at 0, when we know there's at least, 14.7 psi at sea level, then that means that is gauge pressure, because somehow they've taken out atmospheric pressure, right? You understand? If you go over there and you see one that's got it already up here, if you go see one that's already got a reading of like wherever you're at, that 14.7 psi is the average pressure at sea level. So, up here, we might be a little more than that. Well, that's what we call an absolute pressure gauge, because they don't have a circuit that takes out 0 or gives you a 0 reference, right? Does that make sense? So we even have that problem, and sometimes we need to know that, sometimes we don't. So sometimes we need to know how much pressure is being exerted by the atmosphere, and how much pressure is being exerted by my pressure, by my hydraulic pump, or by my pneumatic pump, or my pneumatic pressure. So what we can do with a Wheatstone bridge is we give the ability to establish a 0. Plus we would mount all these things together. So I know in resistors, especially metal film resistors, their output changes a little bit with temperature. So if we mount all these things together and the temperature changes, then all of them are going to change at the same ratio. And if they all change at the same ratio, then 0 would still be 0. So what we're doing with the Wheatstone bridge is we're compensating for temperature change, and we're also it gives us the ability to set a 0. So this gives us a very, Wheatstone bridges give us an extremely accurate output, voltage output of a watt, of a sensor that changes its resistance with what it measures. So we have the ability to do what? Set a 0. And what is it? So this question's on the test, by the way. The ratio of these two resistors has to match the ratio of these two resistors. If the ratio of these, so I could come up here, I could come over here and make this a 1K and a 10K. And then I could come over here and make this a 2K, and I can make this a 20K, and the ratio would be, it's still, the ratio is the same, so this would still be balanced. So here we're not extremely concerned with the size of the resistors. In fact, the larger the resistors, the less current that the Wheatstone bridge will have. So if I keep the ratio the same, so R1 divided by R2, if it's equal, if I come up with the same fraction that I do, if I take R3 and divide by R4, then the bridge is balanced. If they're not the same, then we should expect our meter, we should expect to get a voltage out of it. And by the way, it'll also go negative.
So if this is 5 volts and this is 4 volts, then this will measure negative. If this is 5 volts and this is 4 volts, this will measure positive. So with a temperature sensor, I would actually be able to tell when it's below 0. So now we know, now we have a capability of measuring not only positives, but we have the ability to measure negatives with a Wheatstone grid. Voltage divider, you would do that. So all it's going to do if over here, if water measure goes up, the resistance is going to go up, resistance is going to go down. Well, is that a minus 5 degrees or a plus 5 degrees? Well, we don't know that. Then we have to figure out what we call a transfer function with what these voltages over here mean. So this is what we still bridge. So it can give us what? It can give us both a negative and positive measurement. It can do what? It can compensate for temperature, and it gives us the ability to set a 0 reference. Now we've got some PLCs over there. The Compact Logic actually has got a resistance into it, so they've got this inside the PLC. Oh, just did that. Everybody okay here? So this is a control system. We have input, we have control, and we have output. So our control in this class is going to be relay logic. Our inputs, of course, are going to be our sensors. And our outputs, of course, are going to be relays here. In the programmable controllers, your logic would be your programmable controller. So what does programmable mean? And then not only can you program it, but you can change the program, right? So the problem we have with relay logic, if we want to change what the circuit does, we have to rewire the circuit. On PLCs, if we want to change what it does, normally all we have to do is reprogram it. So this is one of the main reasons that these are dominating the control section now on new lines. Is everything going to be PLC? No, it's not. We're still going to have a lot of relay logic out there, especially on older applications. That's what I love about US Steel. You know, they've been around so long that they had real low stuff, and you figured out how they did it. It was neat. And then, of course, the newer stuff. In fact, when I worked out there, I think we only had 2 PLCs. The actual computer control was done by computers. By many computers. So this is basically before PLCs actually came into being. PLCs have been around a long time, but they originally moved into the auto industry. Okay, guys, I'll take a 2-minute break. Wheatstone bridge control system. So we know the inputs are going to be most of our sensors. When inputs can be manually operated, these are your push buttons and stuff like that. This is the basic setup of 2 systems we'll have to look at. We have what we call an open loop system. Also, some people refer to it as non-servo. And then we have a closed loop system, which is also referred to as a servo system. So one of them, we have something called feedback. The other one, we don't. So a closed loop, an open loop system is we tell it what to do, we take it for granted, it's done. A closed loop system means we tell them to do it and then we verify that it's done. So most of ours are going to be open loop systems. So we'll put the sensor over on the left-hand side, and then we'll run it into a relay, and it's going to turn on a light. But we're going to make it a closed loop system because we're going to be the feedback, right? You understand? But if there's nobody in there, it would, if you weren't looking at it, you would take for granted that it was done. A closed loop system or a servo system, we tell it to do something, then we verify that it's done. So your cruise control is on your car is a control, and your vehicle is a closed loop system. So you're going 80 miles an hour and you engage your cruise control, and then it knows if it's going too slow, it didn't know if it's going too fast, so it's a closed loop system. My motorcycle had a throttle lock on it, and I had to install it. So if anybody rode a motorcycle, your control is on your left-hand side, right? And if you control the speed, well, after a while, you're going 100 miles, your arm will go to sleep. So you could buy a throttle lock, you just lock the throttle and it wouldn't move. But the problem is, it worked real good if you was going on flat, but if you went up a hill, your motorcycle would slow down. If you went downhill, it would slow. Well, that was basically an open loop system, right? You understand that? Of course, now I guess you can buy motorcycles, especially those three-wheeler motorcycles that probably have cruise control on. Those things are almost like cars. And that's what they call it, Spider. That's a motorcycle that it's classified as a motorcycle. So to get automation, to have automation means we produce a product with little or no human intervention. We're going to have to depend on closed loop systems. But if we're not, of course, a closed loop system is going to be a lot more expensive than an open loop system. So if they can do it open loop, they're going to do it open loop. If they can't do it open loop, then they'll do it closed loop. Are we okay? Does that make sense? Any questions? So we establish a set point. So that's what you're doing on your cruise control. You're going a certain speed. When you engage it, that's what our system is attempting to go. And then we have some type of sensor that provides us feedback. You're making me cough here. Which gives us feedback, which tells us that it's met the set point. It's either above the set point or below the set point.
Which control system constantly monitors the output?
That's the servo system, or a closed loop system. Any more questions? So automation depends on closed loop systems. We tell it to do something, and then we verify that it's done. If it's done, then we move on to the next section, right? Understand that? You'll see that a lot if you take the AUT 208, the troubleshooting class, where we actually move over. And toward the end of the semester, we'll go over there. We'll meet one of our classes over in H111, so you can see a system in operation. That depends on a closed loop system. So AUT 208, we've had some people that have taken it here, so y'all might want to talk to them. This is a pretty class about these, of course. And it deals with the So like I said, if they can do it if they're going to do it open loop, they're going to do it open loop. If they can't, especially if it's automated, then they're going to move to a closed loop system. But the problem with closed loop systems is they cost a lot more money, right? And just to provide the feedback. We okay? So questions? How we doing? Pretty good? Okay, so if you got this open, don't call these out. So that's cheating. So what's some of the things that we might want to sense in the control system? So if you're looking at the PowerPoint, the next PowerPoint, don't read it. What's some of the things that we might want to see?
Yeah, sensor, might want that sensor. We already talked about that, right? Object. Yeah, location. We have two. We have a location. If it's added location, we're going to refer to these as proximity sensors. Proximity, and then we do have position sensors, which actually senses. So a proximity sensor senses when it's at a spot, right? I understand that. A position sensor would sense it within a range. When you walk into a store now, you can come in at different angles. So what it's doing, it's sensing your position, right? It's not sensing if you're technical. I don't know about that. Go ahead, any more? Right. Any more? Huh? Density. More?
Talking material is made out of metal or plastic.
Yeah. So they do this in the lumber business all the time, where they, people drive nails and everything into trees. I saw a railroad spike that had grown inside a tree. And if they let their, the $1,000 saw blade go through and hit that railroad spike, so just if you go there, they send it all the way through a thing that detects the metal. All right, what else? Yeah, we could do length. That's a good one. Or probably it'd be probably more would be size. Would be size. Any more? What's that? Oh, yeah, we can sense light. I have that at my house. So, I've got motion detectors around my house. They don't come on during the day. Even though they sense motion, they don't come on during the day. So it's got a light detector in there. And our a lot of our street lights used to, before they came out with the light detectors, you'd drive around to these parking lots, and when it started turning summer, their lights would be on because they'd had them set for the winter, and they'd actually have to go back and reset the time when they went off. But now they don't do that because they sense when it's what, when it's day and night. Any more? Yeah, what do you sound? Sound would be one. Any more? Yeah, wait. Yeah. We worked at, we had an electronic scale. I worked for a scale company for a while. Worked on all the electronic scales. And the Go Food dog plant down at, in Birmingham. Is it still on First Avenue down there? That was the grossest place to work at. But, they would sense if the cans were full or not full. They would drop them into a water. And if they weren't full, they would float to the top. They called them floaters. And I like to go out there because they'd give me all the floaters. And the cans wasn't full, but so they just run them. And if they moved along the conveyor belt on the bottom, it meant they were full. But if they floated to the top, so I worked with weights for weight sensors for a long time, and we'll look at those. Any more?
What is sending maybe like water or gas?
That would probably be material, but yeah, we could sense, the type of material it is or object it is. It could be gases, but that's good. Any more? I will sit inside.
Maybe when it needs to stop and start. And the control system.
That would probably fall in one, this would sit, all these would probably sense that, you know. If an object is there, we might start it. If it's not there, we might stop it. So what we're trying to do is figure out, so time, most of our programmable controllers have what we call real-time clocks in there where we can make things happen, you know, every Tuesday or every 12 hours. So yeah, so time. Any more? So this is what our classes usually come up with. Position, speed, weight, count. So nobody brought up count. Pressure. Nobody brought up pressure. Flow rate. Flow sensors. Temperature. That was brought up. Light. Thickness. How thick something is. We have out at US Steel. We had an X-ray machine that measured the thickness of the galvanizing codes that they would put on metal when they galvanized it. That was the first time I ever got to work with X-rays, by the way. Since time, somebody brought that. Gas levels, so somebody brought that up. I didn't write it. Liquid levels, so the levels of objects, right? Motion. I actually mentioned that, you know, that we have motion detectors. Orientation, shape and size, we brought that up. Proximity at a certain location. Moisture content, viscosity, which would be the thickness, the actual thickness of liquids, and that's what we can look at. So the ones we're going to look at is, of course, we're going to look at
Viscosity, the thickness, would that be the thickness like from oil or water, that thickness?
Yeah, so the thinner it is, the lower the viscosity, the thicker it is. It is. Now, you know, we have mixed viscosities on our oils. So 20-30. So what it is, it's actually a combination of an oil that's real thin at extremely cold temperatures, and then it moves over to the other one when we get into hot temperatures. So used to, you know, you buy oil for your car, it was a single weight, and you'd get out there in the wintertime, and it would do what? It'd go because all that oil was so thick. So that really helped. So we're going to look at position sensors, speed sensors, weight sensors, pressure sensors, flow sensors, temperature, light, motion. We'll get into orientation, proximity. I don't think we got any viscosity. Oh, and level sensors. So we'll look at these two. So these are the ones that we'll talk about. Are there more? Sure, there's more out there. You know, that senses different things. So this is just what we've come up with in the past. I don't think there was anything that was brought up that's not somewhere in the list. We'll start off with position sensors, and then we'll move into proximity sensors. I think that's second. We'd have to look at the modules and see, but these are the ones we'll look at here in the semester. We're going to do labs on position sensors. We don't have any speed sensors. Well, we do, but we don't have enough for the class to look at that. And we have to know how to use an oscilloscope to show that. So I'll show y'all one that would use a speed. A couple of them. I'll show y'all a path generator, and we'll look at some encoders. I don't have anything to show you weight. Count. We don't have any counters over here. We used to have one around here. But, pressure, I've got some pressure sensors I can show you. Flow sensors I don't. Temperature sensors, I can show you some RDT, some resistors, but there's still some more out there. We'll do a lab on light sensors. We'll do a lab on position sensors. We'll do a lab on proximity sensors. We'll do a lab on pressure sensors. And of course, the rest of them we'll just have to learn about. any questions on what we did? So we're not quite ready. We should be able, toward the end of the class, we'll give y'all out the lab procedures. So, you need to make sure, next class that you bring in your lab supplies. So what do you need to have for lab? Have a meeting